Okay, before we get into what's going to be on the unit exam, okay, a couple of things about getting ready for it. Physics is very much like chemistry in that it is very skill-based. You need to be able to demonstrate things to me, demonstrate your ability to solve acceleration problems, interpret and calculate things from graphs, okay? Solve conservation of energy problems. It's all about demonstrating what you can do. Okay, the bulk of the marks on this test, and by the bulk I mean like at least 80% of them, are demonstrate to me that you can do this. Okay, so make sure that you are, as part of your studying, a large part of your studying, doing practice problems. Okay, there's one thing you're going to do that will help you prepare for this test. It's doing practice problems on the things that we have solved problems on in class. So graphing, V equals D over T, acceleration, okay, work energy theorem, conservation of energy. Okay, expect that you will see problems just like the ones we have done on your quizzes on the test. Okay, nothing different. Okay, just like those. All right, the ones on your worksheets, just like those. All right, that's the kind of stuff that you can expect to see next Thursday on your unit exam. Okay. Other things to know: you have to have a calculator for Thursday. You cannot use your phone as a calculator on Thursday, so make sure that you beg, borrow, or creatively acquire a calculator, okay, for Thursday. All right, I only have one. I lent out my loaner and I never got it back. So now I only have my calculator left. Okay, if more than one of you shows up without a calculator, one of you is SOL, and that's so out of luck. Okay, we don't want that to be you. Right, so make sure you come prepared. I would also say it would be a good idea to probably just have pencils for this test. Right, since it's mostly problem solving, not a lot of paragraph writing like biology was. Okay, pencils are best so you can erase things. Okay, as you go along if you need to. Right, those would be my suggestions. Have a look over stuff over the weekend. Okay, like I said, problem solving. Okay, I've got the review package that I posted yesterday. There's some good stuff on there. A lot of the stuff on there actually used to be on the unit exam. I just stopped using it because it needed a refresh. Okay, so the stuff that's on there is very much like what you're going to be asked to do. Okay, everything on the test we have done before. I am going to ask you to do exactly the same things, especially stuff from your labs. Okay, your need for speed lab, okay, you had to calculate the acceleration of the cars from the graph by calculating the slope. You had to calculate the displacement of the cars by calculating the area under the line. I'm not going to ask you to do anything different, but I'm definitely going to ask you to do those things. Okay, you're going to have a graphing question on position versus time. That's going to be just like your graphing lab with the carts in the hallway. Okay, I asked you to calculate slopes. I asked you to calculate total displacement. Those are the kind of things I'm going to ask you to do. I'm going to ask you to use y equals mx plus b. Okay, make sure you're able to do that. Okay, understand what each part of it represents on each graph. Right, that's the kind of stuff we got to go over. All right, so when we started out, okay, what we looked at first were the types and forms of energy, okay, and then kind of the people who contributed to the study of said types and forms of energy, okay. That's all multiple choice stuff. It's mostly recall. Yeah, there's a few people's names and stuff in there, so I would go over the notes package part there on the types of energy, like solar energy, nuclear energy, kinetic, mechanical, all that kind of stuff. That there's definitely going to be some questions on that in the multiple choice. Okay, I'm also going to ask you about the kinds of systems. Okay, we had open, closed, and isolated systems. Make sure you know the difference between them. Okay, remember that an open system exchanges matter and energy. A closed system exchanges only energy, and an isolated system exchanges neither. Okay. In terms of the types and forms of energy, it would probably be like maybe like an application type question, like a ball is rolling down a hill. What kind of energy does it possess? Okay, and maybe the options would be like A, solar, B, chemical, D, kinetic, or C, kinetic, D, thermal. Okay, or something like that. Okay, kinetic would obviously be the best answer of those ones on there. Okay, something like that. All right, so understanding what kinds of energy are present. Okay, we also need to know about the laws of thermodynamics. Okay, how a heat engine works, how a heat pump works. Okay, remember that a heat engine, okay, harnesses the fact that energy flows from hot to cold, okay? That's the second law of thermodynamics, and a heat engine harnesses the second law of thermodynamics. As energy moves, so does matter. When matter moves, work can be done, okay? That's mechanical energy. Okay, so that's a heat engine, okay? Remember, heat pumps work against the second law of thermodynamics, okay? They use energy to pump heat into the hotter area, right? So they're like active transport, but for energy, okay? And that's how air conditioners and refrigerators work. Okay, I would also say that you would probably need to be able to explain to me how the laws of thermodynamics dictate that a perpetual motion machine could not only not exist, but even if it could exist, would be completely useless. Okay, I would say that something, being able to explain that would be important. All right, so that was like the first 2 days of the unit, was just that stuff. And then we moved on to scalar and vector quantities. All right, is it possible you could get a multiple choice question that says, which of the following is a vector quantity, A, B, C, or D? Yes, it is. But that's not the most important reason you need to know which things are scalar and which things are vector. It really matters in the written response. For example, if I give you an acceleration problem, and it goes something like a car accelerates from rest at 3.5 meters per second squared for 5 seconds. What is its final velocity? Does your answer need a vector or not? It needs a vector. That's the kind of thing that costs you a mark if you don't remember that velocity is different than speed, and velocity is a vector quantity and thus requires a forward or a positive or something like that on it, okay? And that could happen on a number of questions because we dealt with lots of things that were vector quantities, okay? So knowing the difference between vector and scalar, that's going to be important. It could also be important on your graphing questions, okay? If I ask you, here's a position versus time graph, calculate the displacement between A and C, and you forget to put a vector on it, then you get it wrong because you forgot that displacement the vector quantity. And on top of that, on a position time graph, you calculate distance and displacement differently. Okay, so being able to remember which one's scalar and which one's vector is important. Okay, not just for which ones are scalar, which ones are vector. All right, that same day we talked about, sorry, these were our scalar quantities: speed, distance, time, energy, and work were all scalar. Okay, vector quantities were velocity, displacement, acceleration, and force. Okay, and then we did some problem solving using V equals D over T. I would not expect a written response item out of 5 marks on velocity on V equals D over T. Okay, you'll need V equals D over T probably for some of the questions as parts of them, like especially if it was a graphing question, it might be needed in there. But mostly any calculations with V equals D over T would be in the multiple choice, okay, because they're a pretty simple calculation. Like, could get something like this, let's say. Person is driving through a parking lot looking for a space. They drive 50 meters north, then turn and drive 20 meters south to an empty spot. What is their average velocity if this took 30 seconds? Right, well, then you would have to go find the displacement, divide by 30 seconds, and you have the velocity. Okay, some kind of simple calculation like that. Okay, expect that that would be a multiple choice item versus a 5-mark written response question. Okay, everybody all right with how those work? Okay. Remember, guys, V equals D over T. This is speed equals distance over time. Okay, and that in this case with the arrows over top, this is velocity is displacement over time. Okay, remember also that to calculate displacement could be final position minus initial position. That would be important if you were looking at a position versus time graph. Okay. From there, we went to graphs. Now, graphing is huge, right? The two biggest topics, marks-wise, on your unit exam are graphing, number one, work energy theorem, number two. Okay, so graphing is the biggest, and it's the biggest by a significant margin. Okay, it probably comprises 1/4 of the marks on the test. Okay, just graphing. There's a number of multiple choice questions about graphing, and in the written response, there is a position versus time graph and a velocity versus time graph in the written. Okay, and there's multiple questions in the multiple choice about graphing. Okay, so what are you going to be asked to do with graphs? Well, if it's a multiple choice graph, it would be either a very simple calculation, like it's a position time graph and I ask you to calculate the displacement, it's, final minus initial, something easy, or it's an interpretation question. Here's a position versus time graph. What is the object doing during the first 5 seconds? And you would have to interpret the shape of the graph and answer the question correctly. Okay, that would be the kind of thing I would ask you to do in the multiple choice, interpretation and simple analysis of the graph. Okay, so if we are looking at, you know what, I'm just going to delete these so that I can make more sense of it. I've scribbled too much on this. All right, if I have a position versus time graph, and let's say my position versus time graph looks like this. Right, so this is meters, this is seconds, and I even have beside it that y equals 2.5 times x plus 1.2. All right. What is that object doing? It is moving at a constant velocity. What's that? In a positive direction, yes. All right. What is the velocity of this object? 2.5 meters per second. Okay, how do we know that? Right, this was our graphing lab, right? We discovered in the graphing lab that when we manipulate for m, it's y minus b over x. On the y-axis are the positions, final minus initial, and on the x-axis is time. Okay, so the slope of the line on this graph represents the velocity of the object. Now, if I'm asking that on a test, and I give you this graph and that equation, and I say exactly that, what's the velocity of this object? How many marks do you suppose that's out of? 1, because it requires no work. Okay, be on the lookout for that when you're doing this test. Every time you do a question, at the end of the question, I always put the mark in brackets. If it's out of 1, there's no calculating involved. Okay, it's simply you need to recognize that the answer is there. Okay, always be on the lookout for that, because sometimes people look at a question like, I have no idea how to do this. I have no idea what to do. Look at what it's out of. If it's out of 5 marks, you're in trouble. If you have no idea what to do and it's out of 5 marks, you have a lot of stuff you don't know how to do, because 5 marks is a lot of calculations. If it's out of 1 mark, that's good news. The answer's in front of you somewhere. Just find it. Okay, does that sort of make sense? It's a good test-taking strategy. Look at what a question is out of. All right, because you wouldn't believe how many times I ask a question like that, I put that it's out of 1 mark, and people do 5 marks worth of work to prove that they don't know what the answer is, and they end up getting nothing for it, okay, because it wasn't the right stuff. All right. Okay. Another thing that a question like this might ask could be, how long will it take the object to reach a position of 20 meters? Okay, if I ask that, how am I going to solve that? I'm asking you to find a position. Sorry, I'm asking you to find out how long it will take to reach a certain position. Which axis is position on? Y. Which axis is how long on? So what am I asking to find? X. Yeah, I'm asking you solve for an X value when Y is 20. Okay, how long will it take it to reach 20 meters? Y is 20. Solve for X. Okay, guys, a question like that will sound like this. Using your graph, and that part will be bold-faced, italicized, and underlined. Using the graph, do this. Okay, that means use that. It doesn't mean use V equals D over T. Why will V equals D over T give you the wrong answer? Because it will not include that. Okay, if you use V equals D over T, it will not take into account the y-intercept. So if it says using your graph, use your graph. Okay. All right, other thing the question could ask, what will be the position after 100 seconds? Okay, so in this case, I've given you an X value. I'm asking you to calculate Y. Okay, so being able to use the graphing equation, which you're doing in math right now anyway, okay, is something that you're going to be asked to do on this unit exam with either the velocity versus time or the position versus time graph. Okay, you can only use this if the graph is one single line. If the graph is many parts, then that doesn't work. Okay, so if we have a position versus time graph that doesn't look like that, let's say it looks like this, okay, then you're going to be asked to do other things. Like maybe for 1 mark, the question will ask, what's the total displacement of this object? 0. Okay, how do I know it's 0? Well, the initial position is 0, and the final position is 0. So total displacement is 0. Okay, this question could also ask, what's the total distance traveled? And then I'd have to go, okay, how far did I go here? I didn't go anywhere here. How far did I go here? I didn't go anywhere here. How far did I go here? Okay, and do those calculations. Again, all things that we have done in class multiple times. Okay, I'm not going to ask you to do anything we haven't done in class. Okay, and I'm also not going to give you graphs like we did in class. Like we had that one that had like went all the way up to like J. It had like that many line segments on it. That's just going to make the test take forever. Okay, I just want to know whether you can do it. You're going to have a graph that at the most would have 3 or 4 sections. Okay, and that would be it. Okay, what if I have a velocity versus time graph? Say it looks like that. All right. Question asks me, what's the acceleration of the object in the first 2 seconds? Right? Would I be able to calculate that if I knew that this was 5 and this was 0? Yes. Okay, then I would just use this. Okay, which incidentally is also going to be the what of this line? The slope. Okay, so if you got a velocity versus time graph that was just one line, remember the slope on that graph is acceleration, because that's where we get that formula from. That's y minus b over x. Okay. What if the question asked you to calculate the total displacement? Then I've got to find the area under the line. Okay, that's going to be average velocity times time. For this part, that's easy. The average velocity is 5. The time is 7 seconds. This is 35 meters. For this part, we go from 0 to 5. So the average velocity is 2.5, or half the height times the base. Okay, this would be 5, right? And off we would go. Okay, so our total displacement would be positive 40 meters. Okay, ringing a bell? Graphing is huge. Okay, it's like Trump. Huge! Huge! That's how big it is. Okay, it's like the wall that never got built. Okay, all right. Then acceleration. So once we got done talking about graphing, because doing velocity versus time graphs naturally led to acceleration problems. Okay, be able to solve acceleration problems. There are two, okay, on the test. So make sure you can manipulate and solve for those. Okay, and then work energy theorem. Right, so expect to get some problems where you're going to have force times distance on one side, change in either potential or kinetic energy on the other side. In fact, expect one of both. Okay, there's two work energy theorem questions in the written response. They're each worth 6 marks. So expect that one will be potential and one will be kinetic. Okay, just like the ones we did in the examples. Okay, for this one, guys, I would focus more on the examples I did in class than I would on the examples on the worksheets. All right, so I would go back in Google Classroom and watch the podcasts of the examples. We did like 12 different work energy theorem examples in class. Watch a few of those. That's the kind of thing I'm going to ask. Okay. All right, and then conservation of energy. That's what we've been working on most recently. EI equals EF. There's one of those. Okay, roller coaster question kind of thing. Right? And it'll be worth big marks as well, okay? Just because there's so many steps. Okay, the one you had today on your quiz was out of 6, so expect that the one on your test is probably out of around 6 marks. All right, and then the one thing that we haven't talked about yet that we're going to talk about tomorrow is efficiency. Okay, and efficiency is just the percentage of the work you put in that actually does useful work. All right, and we just haven't talked about that yet. Okay, but in the real world, obviously, you know, the initial energy and the final energy aren't equal. We lose a bunch of it in the middle because things are not 100% efficient. It turns into other kinds of energy that are not useful. Okay, and that's what we'll be looking at tomorrow. Okay, it's a pretty short lesson. It's pretty easy stuff. All right, questions from you guys? Anything you want me to go over in more detail or questions that you have that you'd like me to answer? Okay, so your test has 20 multiple choice questions and 7 written response. Two of the written response have multiple parts, so they're like A, B, C, okay? And the written response is out of 45 marks, the whole test is out of 65, which actually makes it one of your shorter tests, okay? Chemistry was out of like over 70, okay? Actually well over things, it might even been out of 80 something. Okay, biology was out of 70 something. So okay, this is shorter in terms of marks, but obviously there's problem solving to do, math to do. It takes a little bit of time. Okay, so like we said, in the multiple choice, okay, expect things like what work is and what energy types there are. We talked about that. Okay, definitions of the different kinds of energy, laws of thermodynamics. Okay, first law and second law, types of systems. Okay, heat pumps and heat engines, scalars and vectors, V equals D over T, simple calculations to do with that, interpretation of graphs. Okay. Simple acceleration stuff, more stuff on thermodynamics and energy, and there's an efficiency multiple choice question. And then in the written response, okay, position versus time graph. Okay, acceleration, velocity versus time graph, work energy theorem, work energy theorem, conservation of energy, and acceleration. Okay, so 2 acceleration, 2 work energy theorem, conservation of energy, and 1 for each type of graph. Okay. All right. If you guys don't have any questions for me right now, that's fine. I would suggest then that you have a look over the review package. There's a lot of sample questions on that that would be worth you trying. Okay, so you can see here on the review package, I've got kind of what we did today, okay, which is the key points, okay, some of the skills you're going to have to demonstrate, problem solving and graphing, okay, and then there's some review problems and activities. So finding definitions, okay, there's a fair amount of that. Some stuff here that's from the first lesson on the mechanical energy and things like that. Thermodynamics, and then there's some problem solving. For the problem solving, I do have the answers on here. Okay, so you'll know if you did them right or not. Okay, if you're doing them on the weekend and you're not getting these answers, then that's probably something you should come and ask me about. Okay, so like I say, these all used to be on the unit exam. I just don't use them anymore. Okay, just made up new ones. So they're exactly the kind of thing I've asked in the past, right? Same as this problem. Okay, and then I've got a couple of graphs here as well. Okay, these ones used to be on the exam. They're not anymore, so they're like what I would ask. Okay, gives you a pretty good idea. Ethan, question? Yeah. Okay, so with the heat engine, okay, so for a heat engine to work, there has to be a massive difference in thermal energy between one side of the engine and the other. Okay, so for a heat engine, there would be like the engine part right here, which would usually be some kind of turbine, okay, or something like that. Okay, over here, hot, over here, cold. As energy moves, according to the second law of thermodynamics, from hot to cold, okay, it moves matter with it. Okay, that matter goes through the heat engine, causes the heat engine to turn, and that can be used to do work, to do useful work. Right? This stuff, the hot would go to the cold no matter what. All we're doing is harnessing that. We're putting something in between and making it do something on its way there. Okay? We can't really stop the second law of thermodynamics. That's the way things want to go. We're just taking advantage of it. All right? We do the same thing with a hydroelectric dam. Right? We're taking advantage of the fact that gravity wants to pull water from a high height to a low height. So where there's a waterfall, if we put a turbine in the waterfall, that's a hydroelectric dam. The falling water turns the turbine. We can't stop the water from falling, but we can take advantage of it when it does it. Okay? For a heat pump, okay, this is the hot, okay, this is the cold, and what we're doing is we're using energy, okay, to pump heat this way. We're making it go backwards. Okay, we're disobeying the second law of thermodynamics, but we're doing it by paying for it. Okay, we're essentially paying to go the wrong way, right? And we're taking heat from a cold area and pumping it into the hot area. That's not the way it wants to go. It's like making water go uphill. If you want to make water go uphill, you have to fight gravity. In this case, you have to fight thermodynamics. Okay. Good. Okay, any other questions? Okay, well then have at her with the review thing here. Okay, that's on Google Classroom, so you can check it out on there, or you can look at it here, but up to you. If more questions come up, then please ask. Okay, you got the rest of the class to kind of look over that stuff and do some practice problems and such.